Let's put our understanding of heat and work together to see what happens during an isothermal expansion of a gas. Isothermal requires that we keep the temperature constant. In the laboratory, the way we do that is to stick our experiment, our apparatus, into a constant temperature bath. So in this case, since we're going to expand a gas, we'll put our gas in a piston system and we'll immerse that piston in a constant temperature bath so that we have a reservoir. Our surroundings will consist of a reservoir which maintains a constant temperature. To expand the gas, we're going to release the external pressure slowly so that the internal pressure and the external pressure remain the same throughout, so that we do this reversibly. And as we decrease the pressure, the piston will move up because the pressure has decreased and the volume must increase. Because we've increased the volume of the system, we can see that we have done work on the surroundings. So energy has left the system as work. If we lose energy as work, we have less energy available to our system and therefore less microstates populated and a lower temperature. But we said we were going to do this isothermally, and so to keep the temperature constant, some heat from the reservoir must enter the system, so we increase the energy of the system by adding some heat. That keeps the temperature of the system constant. So we do work on the surroundings. The energy lost as work is compensated by heat that is input from the surroundings. The first law tells us that the total change in energy of the system is equal to the amount of heat input from the reservoir plus the amount of energy lost as work to the surroundings. Because energy is a state function and therefore an exact differential, I can also express the small incremental change in energy of the system as the partial derivative of energy with respect to temperature at constant volume times the change in temperature plus the partial derivative of energy with respect to volume at constant temperature times the change in volume. But I know that the change in temperature is equal to 0 for my isothermal expansion. Let's take a look at the derivative of energy with respect to volume at constant temperature. If we have an ideal gas, there are no interactions between particles. And so if I change the volume of the system, all I'm doing is moving the particles closer and closer together. If there are no interactions, then this does not increase the potential energy of the system, and it can't increase the kinetic energy because all I'm doing is moving the particles closer together. Therefore, the partial derivative of energy with respect to volume at constant temperature for an ideal gas is equal to 0. I cannot affect the energy of the system by moving the particles closer together. Thus, the partial derivative of energy with respect to volume is equal to 0 for an ideal gas, and so we can say that dE is equal to 0 for the isothermal expansion of an ideal gas. And so when I expand an ideal gas isothermally, the small incremental amount of work is equal and opposite to the amount of heat that has to enter the system to balance the temperature. If I have a real gas, I still have the first law, which tells me that the total amount of energy, change in energy of the system, is equal to the amount of heat input from the reservoir plus the amount of energy transferred out of the system as work. In addition, the expression for the incremental change in the energy with respect to the partial derivatives is still a very general expression. And since we're doing this isothermally, dT is equal to 0. However, in this case, dE dV at constant T does not equal 0 because we do have interactions between particles, and when we push the particles closer together or pull them further apart, we're changing the intermolecular potential energy and thus the total energy of the system. So we can express the change in energy of the system as equal to this derivative of energy with respect to volume at constant temperature times the change in volume for the isothermal expansion or compression of the real gas. This is also equal to dq plus dw according to the first law. Solving for dq, we can see that dq is equal to the partial derivative of energy with respect to volume at constant temperature, dV, minus dW. And so dQ, in this case, for the real gas, is equal to the amount of energy required as heat to keep the temperature constant for the ideal case, plus this correction for the gas not being ideal. The correction for non-ideality is essentially the amount of work required to break up the attractive interactions between particles as the gas expands. So we can see now that the amount of heat required to compensate for the energy lost as work is greater in the real case because we need to supply some energy to break up those intermolecular interactions.